Welcome back to another HVAC-Engineering-Techie training video. Today we're going to talk about HVAC commercial special air systems, which could be induction boxes, chilled ceilings, chill beams, displacement ventilation. Things that don't fit in the other videos are here. So remember, this channel is a channel that talks all things HVAC, engineering design, construction, equipment, systems, test and balance extensively, controls, efficiency, and performance. So these training videos are intended to help you advance your career. Before we start, I'd like to ask you to become a subscribing member if you're not already. It doesn't cost anything. It's absolutely free. Just have to click that subscribe button down below. And the reason is that, and give me a thumbs up. The reason is Google uses those to judge these videos. And so I'd like to keep doing these for you. So if you do that for me, I'd really appreciate it. That keeps us going. So let's get started on HVAC commercial systems. All right, first we're going to talk about induction terminal units. Induction terminal units are normally used where we have cold air supply comes from the air handler. Normally these were used a lot when we had below 40 degree air, 35 degree, 38 degree air, which are coming off normally off ice banks. Could be just a low temperature chiller, but what happens here is that the cold air comes in, and it has a baffle plate in here, and it runs by the baffle plate and creates a negative suction right there, and that induces plenum air to come into the box here, and then that air together comes out this way. And the amount of air here is adjusted using this damper plate, which either provides more air or less air to this baffle plate in here. So induces return air to temper the supply air. So that's an induction box system. We don't see them a lot anymore, but you might run into them in the field every once in a while and see what they are all about. I mean, you might assume they're a series box, but remember, they don't have a fan. That's the way to tell them. Displacement ventilation. Now, this is something that has become popular over the last 15 years or so. And this displacement ventilation is very clever, and it does work, but it's a little bit different to try to set up. So what happens is you have an air handler in the room, and this air handler sucks air in off the ceiling, return air, up through the unit, puts it through the coil, back down into the space, but instead of dumping it into the air stream, it dumps it down at the floor. And the idea is to create an envelope of colder air down at the floor level. And this is low velocity. We're not speeding it very fast. This is very low. It just sort of dumps it onto the floor so it'll stay down there. And then what happens is the cold air blanket's floor is about 70, 72 degrees. It's not real cold air, but it's cold enough to keep it in the bottom. And then the heat generated in the space causes the cold air to rise. So people actually are one of the warm things in the air. So the heat around the people going up like this actually draws the air around them. So they actually creates a fresh air envelope around a person. It's about 2 to 3 inches around a person as it sucks it up. Or if you have a machine or whatever, anything in the space that's producing heat will draw this air up as long as it's down here. You know, if it's something on the ceiling that doesn't do that, but that's what this is called, displacement ventilation. Heat of the people causes the air to rise around them, providing fresh air. So this is used for things that have space where the fresh air to the people is more critical, like casinos where smoking is allowed. This has been used extensively in casinos where, you know, this keeps these people smoke free. Even if there's smokers 20 feet from them, you won't be affected here. Now, of course, if you're standing next to a smoker, you're going to be affected, but not if that. And also movie theaters and arenas and things like that, they use this here cold air. Now, we have used this in offices also, and that does work, except it's a little more critical in an office because a person is sitting down and will be in more of this airstream, which is not as effective if people are standing up. So this is called displacement ventilation. This works really well for CO2 because the air around the person is the fresh air. The air over here is the not so fresh air. So this works really good for that, for ventilation, for people ventilation. Chilled ceilings. Now, chilled ceilings came about from Europe probably 30 years ago. And in Europe, they had used these extensively, and we started using them here. And there was a lot of resistance to using them because people said, oh, this can't be because you're going to rain inside the building. Well, it turned out that's a fear that's unfounded because we control for that, but also it doesn't happen very well naturally. People think it does, but it does not. So what happens here is these ceiling panels have a copper pipe adhered to the back of them, and these are aluminum panels that are made to look like a ceiling tile, and they can be made any way you want them, but they look good, but they're actually made out of metal and not fibrous material like the ceiling tile. So what happens is the heat of the room radiates up to this cold plate. This plate is cold, and it's radiation, but it's negative radiation, so it's absorbing heat from the space. And this just lays in a regular ceiling tiles, nothing special, except the one thing that's interesting, because I've installed several of these, is that people don't realize they're there. And we've had people come up and try to open the ceiling by raising a tile, and that doesn't work very well. These have flex hoses on them, but they'll only flex 4, 5, 6 inches. You can't take a tile and move it way out of the way unless you prepare for that. So we've had people damage systems by trying to get a tile, they're fighting a tile, trying to get it out of the space, and they actually break a hose, which is not a good thing out of chill water system. So these ceiling tile, these chill ceiling plates normally cover almost all the ceiling space unless it has something else in it. You know, if it has a light in it or a fire sprinkler head, you can't put, or a speaker, you can't put a chill ceiling tile in something that has something else there. So when we first started using these, we had a little bit of a problem, and that we didn't have enough space to absorb. Now remember, these absorb only sensible heat. They don't absorb latent heat. So only sensible heat. So what the idea was is to have enough of these in the space to take care of 100% of the sensible load, and then you have a fresh air system taking care of the latent load. And normally the fresh air system we prefer was displacement ventilation. So we had that system putting the cold air on the floor with the fresh air required in it, and it would take up all the, we'd dehumidify that air, so it would take up all the latent heat load, and these would take up the sensible load. Well, sometimes we didn't have enough ceiling space, you know what I mean, because there was too much junk in the ceiling. So we started trying to have people put same things in the same tile. Like if you're going to have loudspeakers, put them in the same tile where you have a fire sprinkler head. We can't get it in anyway, so put other stuff there. If you need light sensors, try to put them all in the same so we can have more area. But even then, sometimes we didn't have enough area. So what we did is we upsized the ventilation system to be enough to take care of the excess sensible heat. A couple of times we've actually put these on the walls for that. It's a little harder to hide them on a wall, but you can't do that. So the way these work, of course, is that we have chill water coming from the chill water plant, and it comes into a mixing valve. And this mixing valve says we have a pump that's circulating the water. And what we're doing is we're maintaining this water 1 degree above dew point. And by doing so, these will never sweat. They cannot. And there's also a little, I don't show it in this diagram, but there's a little switch on the back of these. It's really simple. It's just 2 pieces of wires on a felt pad. And they sit there, and if it starts sweating, it actually will sweat on the plenum side faster than it will the room side because it's warmer, and it will get them wet. The minute they get wet, we shut this valve. So basically we have a switch to never, ever let them sweat. But the idea is to use this water, very low velocity, very high temperature, so it's going to be, you know, in the range of probably 65, 62, you know, it's going to be up in those kind of numbers. And we'll cool the space with those. Why would we want to do this? Well, number one, they have some real advantages. One is energy. They're very, very low energy, because most people don't realize that fan energy is one of the most energy hogs in a system. So we don't have that. We have a little bit for that displacement ventilation. Remember, it's very low velocity, very low pressure, so it doesn't use a lot of energy. And 2, these are very quiet. Once you've been in a chill ceiling space, you notice right away when you're not, because all that noise comes from the air conditioning system. There's a ton of noise coming from, and it's very clean. We're not dumping air out of the ceiling So if you're in a restaurant, this is a perfect system for a restaurant. There's no air flowing to get food dirty, nothing dropping on the food. It's very comfortable, and it's very, very comfortable. The radiant cooling effect of taking the heat and radiating it up to a cold plate is very, very comfortable. So these have a lot of additives for one, low energy to very, very comfortable. So that's why and of course, very quiet. So people got them, really liked them, but they're just so different that people kind of reject them. So what's happened is these basically have gone away in favor of chill beams, because this is the predecessor to chill beams, and we'll talk about that in a second. So a typical sequence here is the zone pump shall run and the displacement ventilation system shall be run anytime the system is in the occupied mode. Modulate the chill ceiling chill water valves to maintain room temperature. The chill water supply shall be controlled to 1 degree above room dew point temperature to prevent condensation. Modulate the displacement air handler chill water and hot water valve to maintain supply air duct temperature set point. Upon air handler startup, the supply air temperature set point shall be set to 70 degrees and reset based upon the load. Every 5 minutes, poll the room temperature sensors. If any circuit chill water valve is more than 95% open and the room is more than 2 degrees above set point, decrease the supply air temperature set point 2 degrees. If no circuit temperature control valve is above 60% open and any room is more than 2 degrees below set point, increase the supply air temperature set point 1 degree. Reset range should be between 58 and 78. So what we're trying to do is we're trying to maximize the load from the water and not the air, if we at all possibly can. If the room humidity rises above 60%, design dehumidification, enter the dehumidification mode by controlling the air handler chill water valve to 55 degree set point as measured at the mixed air leaving temperature sensor. Modulate the chill water valve to maintain a 50% room humidity. Modulate the hot water valve to maintain the supply air temperature set point. If the room humidity drops to 48%, in the dehumidification mode. Monitor the room temperature, room humidity, and chill water temperature. Alarm if any room humidity rises above 65%. We're trying to eliminate possibility of water on the chill ceiling panels. We want an alarm if that humidity gets over 65%. Now, remember that if it gets to 65%, that's going to change the dew point, and so this water temperature changes drastically. So it's going to cut down the amount of cooling in the room if we have high humidity. So if we have a high humidity source, we want to get rid of it through the ventilation system as soon as possible. And these are chill ceilings. Okay, let's talk about chill beams. Chill beams is a natural outgrowth of the chill ceilings. And the reason was, of course, is we didn't have enough area to get all the sensible loads. So some bright individual said, well, let's just put a cooling coil up here, and because that gives us a whole bunch of area. So instead of doing all the ceiling tiles, we can just do some, and we'll take that displacement ventilation system and we'll put it across these grills. Then, of course, it's no longer a displacement ventilation system, it's a regular ventilation system. And we'll make these induction units so it induces the room air across these coils by this air, and this is how this works. This supply air, cold supply air, comes in, whips around here, and while it's doing that, it's creating a negative pressure here that sucks air from the space across this cooling coil, and it goes back out with the air. So that's its induction beams, and they're basically air induction, and they have that cold water just like the chill ceilings, exactly the same that cool the room. So this one here operates the same, it has a slightly different but very much the same sequence, just has different pieces of equipment. The fan coil supply shall run and the outside air damper shall be open at any time the system is in the occupied mode. Modulate the chill beam chill water valve to maintain room temperature. The chill beam chill water supply shall be controlled to 1 degree above room dew point temperature to prevent condensation. Modulate the fan coil unit chill water and hot water valve to maintain the supply duct temperature set point. Upon the fan coil startup, the supply air temperature set point should be 70 degrees. Reset based upon the room load. Every 5 minutes, poll the room temperature sensors. If any chill beam chill water valve is more than 95% open and the room is more than 2 degrees above set point, decrease the supply air temperature set point 2 degrees. If no chill beam temperature control valve is above 60% open and any room is more than 2 degrees below set point, increase the supply air temperature set point 1 degrees. Reset range shall be from 58 to 85. So what we're trying to do is we're still trying to make most of the load come from this water and not from this fan coil. So that's why the sequence is set up to prioritize the water to the chill beams. Typical control sequence for this part: if the room humidity rises above 65% dehumidification, it's a standard dehumidification mode again. Enter dehumidification mode by controlling the fan coil chill water valve to 55 degrees set point as measured at the mixed air leaving temperature. Now there's not a mixed air temperature, it's actually kind of mixed air. It's in the cold beam there, chill water valve. To maintain a 50% room humidity, modulate the hot water valve to maintain the supply air temperature set point. If the room humidity drops to 48%, get out of this mode. Go back to normal mode. Monitor the room temperature, control humidity, supply air temperature, and supply air fan status. Alarm if the room humidity rises above 65%. The same reason as the chill ceilings. We don't want to encourage any condensation on the units to do that. So once the systems are operating, they operate fine. Sometimes they have a little bit of a problem setting up the air handler system and how to tab it, because there's no way you can try to measure these little hoses, but these are normally 2 to 4 inch, so they're really small. And the chill beams are not as quiet as the chill ceiling because they have air running across this diffuser, but they're very popular right now, and a lot of times they're popular, and I'm not sure why the engineer chose them, because he has more than one system in the space, but normally you only need one. So you can also have a chill beam on a VAV box. So this is a VAV, instead of an air handler, instead of this one, which has a fan coil unit, this one just has a VAV box. And these confused me for a while, but what they're doing is they're using the chill beams to pick up a lot more sensible load, so they don't have to have quite as much air, and they're letting this take care of the latent load and using this to take care of the sensible load in the space. So basically its sequence is very, very similar. During occupied schedule, the box shall be indexed to occupied mode. Modulate the box damper to minimum ventilation flow. If any chill beam room temperature increases above the room temperature set point, modulate the chill beam chill water valve open to maintain the room temperature set point, with the chill beam chill water temperature being 1 degree above room dew point. If any chill beam chill water valve is full open, modulate the VAV box damper open to maintain the warmest zone set point. So here what we're trying to do is prioritize the chill water here to be most of the load. So we're letting this be first stage, and this will be second stage. If any room temperature drops more than 2 degrees below temperature set point and the chill beam valve is closed, modulate the box hot water reheat valve to increase the supply air temperature to maintain the lowest chill beam room temperature set point. If any chill beam valve opens to more than 20% open, or any room temperature is more than 2 degrees above temperature set point, modulate the box reheat valve closed to maintain the room temperature set point. So we kind of have to use a two-step process here to get the correct control for heating. Monitor the room temperature, monitor room humidity, supply air temp, and box damper position. Alarm if the room humidity rises above 60% and send a dehumidification signal to the main air handler unit. So what happens here is this has no capability to dehumidify. It has to be done upstream. So if we get this room humidity sensor start sensing a 60%, then we put the main air handler into dehumidification mode, and it has a reheat coil in it, so it can now keep this air where it needs to be. And this coil here can be used for some reset, but it's best used for heating in the space. This is the VAV chill beams. It's exactly like the chill ceiling, except doesn't have a displacement ventilation system. It has a direct air system into the space. Now for the chill beam, chill ceiling panels, you could also use VAV to diffusers in the ceiling, but because we need all that ceiling space, we don't like doing that. We'd rather have them dumped out of wall grills. All right, before I leave chill beams, I guess I'll explain the name. The reason these are called chill beams is because it makes no sense at all, right? They're a coil in the surface. Well, in Europe, when they ran into that problem of the chill ceilings not having enough space, they actually built some box beams that ran through the space below the ceiling, and they put chill ceiling panels on all four sides of this beam, and they called them chill beams. And that's where the name came for chill beams. They then adapted it to these diffusers of the coils. That's why they're called chill beams. All right, now let's look at Laboratory VAV Air Systems. Laboratory systems have biohoods or other kinds of work hoods in them, and they have exhaust. They're hooked into the exhaust systems, and they exhaust air from the room. And then there's makeup air into the room, which does the cooling and heating of the room. And then there's another valve here on this exhaust system, which is a general exhaust, room exhaust. And the idea here is as you move this sash up and down, it changes the amount of exhaust. So what we're trying to do is we want the exhaust in the room to always be constant. But moving the sash up and down makes the hood VAV, variable volume. So what we do is we have these control valves, these VAV boxes on this exhaust system. We have exhaust system valves. And as you open the hood and you get more air out of here, it closes down and it proves less air from here, more air from here. When you close the hood, the sash, you get less air. So this opens back up to get more exhaust air. So between these two, they maintain a constant flow of exhaust from this hood and the general exhaust valve. The room is actually a VAV box, but it needs to be a series box. This really needs to be constant flow. The reason is we're controlling room pressure off the offset between exhaust and supply. If you put a full VAV box in here, it's going to really screw everything up because it's going to vary the room flow. Now, some people have tried to make this exhaust system follow the supply by offset, and these two still work together. You can do that. It's very complicated, very difficult to get set right and to keep right. These all use these special orifice valves that are very symmetric and very accurate and very fast. You can't put a box in here that has the standard old HVAC actuators that take 60 seconds to rotate. Not going to work. These have to be fast acting. Most of these are 15 seconds, 10 seconds to open and close, so they're very, very fast. These originally were pneumatic, which are instantaneous, but we've gone back to electric, and so they have to have fast actuators to work. This is the way they work. They have this kind of Venturi effects around this characterized gate. It's not like a damper. It's a characterized gate, like a gate valve. I mean, like a globe valve, but it's actually an air valve. All right, so that's the way those work. The sequence is a little bit more complicated. Now, another thing that makes these complicated, normally, this box is on the DDC control system for the HVAC. These are on a special system that is not provided by the control contractor. So these are special exhaust hood systems, and they have velocity sensors in them to be able to tell what the inside pressure is inside here. And this maintains these exhaust valves. So this control, and then normally we integrate this into the main system via network connection. So we can talk between them, and this is why it makes it difficult to have this VAV and this VAV. Makes it very, very difficult to keep those. So, it's hard to do. So here's the standard sequence. During occupied schedules, the VAV box shall maintain room temperature set point, and during occupied mode, it shall maintain room setback temperature set point. The VAV box shall either be a series constant volume box or have a restricted flow range to meet offset requirements of the exhaust valves. So in other words, you could have a system where you have a maximum supply from that box, and we have a exhaust that basically makes that offset. And then if you're going to have a VAV box and it goes down, it has to have enough shoulder in there so when it goes down, it doesn't go into negative positive pressure in the room. It needs to be negative pressure. So normally they need to be series constant volume boxes. Modulate the VAV box heat to maintain room temperature when required. Modulate the biohood dampener to maintain flow at the hood velocity sensor. If the sash is up, the box will exhaust more air than when the sash is closed or lowered. And that's going to change the volume out of the biohood. Modulate the room exhaust valve to maintain a constant CFM flow offset between the VAV box and the total exhaust airflow to maintain a constant room pressure. Monitor the room temperature, offset flow, supply air temperature, and box damper position. Alarm if the room offset drops below set point for more than 5 minutes. So again, this is the easy way to do these, to have really constant volume come out of this box. If you have VAV, then these two together and this need to always be differentiated between them by the offset flow. And the offset flow is what guarantees the room pressure. Now, we used to do these with a room pressure sensor, but every time you'd open a door, the pressure would change and this would just go everywhere. So by using offset, it takes that bump out of it. The room pressure does change, but it doesn't affect the system control, which turned out to be much better. All right, that's all the special systems I can think of. There's probably some more I missed, but that's them. So congratulations on making your way through this. I hope you had a good time with that. Don't forget to become a subscriber if you're not already, and I'll have a great day, and I'll catch you on the next one.